Welcome back to the Deep Dive. Today we're digging into, well, arguably one of the biggest headaches in modern AI. It's this thing called the long context problem in large language models.
Yeah, it's a huge one. It's like this invisible barrier. LLMs, they're incredibly powerful, but then you ask them to read, say, a whole company's quarterly report, or maybe remember all the details from a customer service chat that lasted a week.
And suddenly the computational cost just skyrockets. It becomes, well, almost impossible.
Exactly. And we know the technical reason, right? The cost, and maybe even more critically, the time it takes to process. It doesn't just go up a bit with more text, it explodes.
It scales exponentially with the input sequence length, the number of tokens you feed in.
Precisely. And it's not just linear growth. We're talking quadratic scaling. So think of it like this. You double the length of the text you give the model. The core part, the attention mechanism that figures out how important each word is to the others, its workload doesn't just double, it quadruples.
Okay, quadruple sounds bad technically, but let's make that real for someone maybe trying to run a big analysis. What does quadratic scaling actually mean for them?
It means going from analyzing, say, a 10,000 token summary, which might be okay, affordable, to analyzing a 100,000 token document. Well, it's not just a bit more expensive.
It's way more.
Way more. It can suddenly need these huge specialized GPU setups running for ages. Often it just becomes computationally unaffordable. Or you hit these memory limits, activation memory, and the whole thing just grinds to a halt. You're literally paying like the square of the input length in compute.
Right, so it's a fundamental scaling crisis,
Yeah.
basically. Now, our sources today, they propose something really different, a kind of radical sidestep around this whole quadratic scaling issue. It's called context optical compression.
Yeah, it's a fascinating idea. And the mission for this deep dive really is to unpack how the visual side of things, how AI processes images can be sort of borrowed, used as a surprisingly efficient way to compress text.
And the really wild part of sources suggests this compression can be almost lossless, like getting the original text back perfectly, and maybe even mimicking how human memory fades over time.
That's the really intriguing bit, yeah. Simulating memory decay.
Okay, let's get straight into that because honestly, it sounds a bit backwards. Why would looking at a picture of text be faster or cheaper than just processing the text itself?
It really comes down to how information is represented and redundancy. So imagine you have 1,000 words of text digitally. That's maybe, 1,000, 1,500 language tokens. The model has to process every single one, understand all the relationships.
Right, character by character, word by word.
But now what if you just render that same 1,000 words onto an image, like a screenshot of the page? A model that understands both images and text, a vision language model, or VLM.
A VLM, right, just to clarify, it's a model trained on both kinds of data, bridging vision and language.
Exactly. So this VLM looks at the image of the text. And it doesn't necessarily need 1,500 tokens to understand it. It can capture all that information, the words, sure, but also the layout, the structure, maybe headings, density, using a much smaller set of internal representations. We call these vision tokens.
So it's compressing the information visually.
That's the core idea. The compression ratio you get between the original text tokens and these new vision tokens, that's the key insight of optical compression.
So if I'm trying to picture this, if the 1,500 text tokens are like, I don't know, super detailed instructions for drawing each letter.
Yeah.
What are the vision tokens? Are they like recognizing whole paragraphs at once or visual shapes?
It's probably closer to thinking about a really efficient image file format, It's like a high-quality JPEG of the document, but even smarter. The model they built, DeepSeek-OCR, has this component called the DeepEncoder. That's the engine doing the clever compression work. It looks at the image and figures out where the important visual information is, how to package it really efficiently. It turns that high-res document image into this small, compressed internal code, they call it Z, that a decoder part can then unpack.
In DeepSeek-OCR, that's the proof of concept model they built specifically for this.
That's right. It's a VLM designed exactly for this. It's got that deep encoder, which is lore, about 380 million parameters, so pretty powerful but not enormous. And then a smaller, quite efficient decoder part, a specific type called DeepSeek-3B MOE, to turn the compressed code back into text.
Okay, and that deep encoder, the 380M parameter part,
Yeah.
that's the real workhorse here for the compression.
Yes, exactly. And it's designed quite carefully to handle these really big, high-resolution images, full-page documents, without needing a crazy amount of memory during processing. That's super important if you want to actually use this at scale.
Makes sense. And they specifically tested this using optical character recognition, OCR. Why OCR? Was there a reason for that specific task?
Absolutely. OCR is kind of the perfect test bed because it naturally forces the model through a compression-decompression cycle. You feed it an image, which implicitly has a high token count if you thought about it as text.
Right.
And you judge it purely on how well it spits out the original text, which has a lower token count. It directly forces the model to answer that key question. Okay, for this page with 1,000 words, what's the absolute minimum number of vision tokens I need to keep to reconstruct it almost perfectly?
Okay, the theory sounds compelling. Compression via images. But does it actually work?
Yeah.
Is it really near lossless in practice? Let's dive into the numbers, the experimental results. They used something called the Fox benchmarks.
They did. And those benchmarks are specifically designed to test this kind of compression-decompression on documents packed with text. And for you listening, this is where you might have that aha moment about just how efficient this can be.
So what's the headline finding?
The core result is genuinely impressive. DeepSeek-OCR managed to get 97% precision in decoding the text back.
Wow, 97%?
Yeah, 97% accuracy, when the number of original text tokens was within about 10 times the number of vision tokens it used. So essentially, they're getting almost 10x compression with almost no loss of information.
Can you give us a concrete example?
Yeah.
Like how much text squeezed into how few vision tokens?
Sure. So they took documents that had between 900 and 1,000 text tokens. That's a pretty dense page of text, right?
Definitely.
And they managed to compress all that information down using only 100 vision tokens, just 100. And in that specific setup, they hit 96.8% precision.
That's kind of amazing. The decoder part, the language model, is basically rebuilding the entire page almost perfectly from what sounds like a tiny visual summary.
That's exactly what's happening. It's like it's learned to read the super compressed visual shorthand.
So we're tackling that quadratic scaling nightmare, not by making the calculations faster, but by drastically shrinking the input sequence the expensive part has to deal with.
Precisely. You reduce the n in the n squared problem.
But okay, 10x compression sounds like a sweet spot. What if they pushed it harder? What happens if you try to cram, say, those 1,000 words into even fewer than 100 tokens?
Right. They definitely tested that boundary. And this is where it gets perhaps more interesting for future research. When they really cranked up the compression, pushing it to nearly 20x.
20 times.
Yeah, like taking documents with 1,200 to 1,300 text tokens and forcing them down into just 64 vision tokens.
Okay, what happens to the accuracy then? It must drop off a cliff.
It drops, for sure, but maybe not as much as you'd instinctively think. Even at that extreme 20x compression, the precision was still approaching 60%.
60%. Now, wait a second. 60% accuracy sounds, well, not great for actually using it, right? If you're losing 40% of the text, isn't the model just kind of guessing or hallucinating the rest?
That's a really important point. And yes, 60% precision itself isn't good enough for most production use cases. But the reason researchers get excited about that number is what it proves about the method.
Okay, what does it prove then?
It proves that the visual compression approach has serious potential. The fact that you can still retain over half the accurate information, even when you've compressed the input by a factor of 20, it shows the visual modality isn't just throwing away data randomly.
Ah, I see. It's capturing something meaningful, some high-level structure, even under extreme pressure.
Exactly. It confirms that this optical compression idea is a worthwhile path to explore further. It suggests it's fundamentally better than just, say, chopping off the end of the text to make it fit, which is a naive approach. It shows the feasibility of this direction.
Got it. So it's about the potential, not necessarily that specific 60% number.
Right.
Okay. Moving from these benchmarks to how it stacks up against other models out there. How does DeepSeek-OCR compare in the real world, like on standard document processing tasks?
Well, this is where the efficiency really translates into practical advantages. They tested it on OmniDocBench, which is a common benchmark. And DeepSeek-OCR actually beat another model, GOT-OCR 2.0. The interesting part is how. GOT-OCR 2.0 needed 256 tokens for each page it processed. DeepSeek-OCR, using this optical compression, achieved better results using only those 100 vision tokens we mentioned earlier.
So less than half the tokens for better performance.
Yep. And then they have this higher resolution mode, they call it Gundam mode, which uses more tokens, but still under 800. Even in that mode, it outperformed another big model, Minor U 2.0. And that Minor U 2.0 model needed almost 7,000 vision tokens on average to get its results.
Wow, 7,000 versus under 800. That's a huge difference in computational load.
Massive. And it translates directly into infrastructure savings, right?
Absolutely. Which brings us to the production side. You mentioned scale earlier.
Yeah, this isn't just a lab curiosity. They point out that this DeepSeek-OCR model is actually practical for generating training data, like really large-scale data production for training other big AI models.
How much data are we talking?
They estimate it can process something like 200,000 pages or more per day.
Per day. On what kind of hardware?
On just a single A100 GPU, the 40 gigabyte version.
Okay, for anyone listening who manages large AI training pipelines, that's a game changer. 200K pages a day on one GPU means you can build massive, high-quality document data sets much faster and cheaper. It optimizes the whole data engine.
Exactly. It's a very practical outcome.
This efficiency, it opens the door to something even more mind-bending, maybe the most fascinating application they propose. Using this optical compression idea to manage history in conversations or to handle documents that are just incredibly long. They're talking about simulating memory.
Yeah, this is where it gets really cool conceptually. They draw this parallel, and they have a figure in the paper, figure 13, that illustrates it. They compare how human memory naturally fades over time. Recent stuff is sharp, older stuff gets blurry, to how our visual perception gets less detailed the further away something is.
Interesting. Both systems seem to have this built-in way of letting details go gracefully.
Exactly, a pattern of progressive information loss. Recent memories are high fidelity, distant memories are fuzzier, close objects are sharp, distant objects are blurry.
So they're actually trying to build a system that forgets things on purpose. That feels counterintuitive.
Yeah.
Usually in computing, we want perfect recall, right? We don't want data to degrade. Isn't that risky?
It could be risky if it's like critical financial data you need perfectly forever, but think about context in a long conversation. Do you really need perfect recall of the exact wording of paragraph 3 from a document someone mentioned 50 turns ago?
Probably not. Just the gist, maybe.
Right. And storing that gist is much cheaper than storing the whole thing perfectly. So they propose using the model's different input settings to mimic this forgetting. For the really recent important stuff like the last message in a chat, you keep it high fidelity. High resolution image, low compression.
Okay, crystal clear for recent context. Then how do they make the older stuff fade?
This is the clever part. For the older context, they propose progressively downsizing the rendered images of that text.
Downsizing the images, like making the picture smaller.
Exactly. They suggest cycling the image of the older text through different modes, maybe from a large mode down to base, then small, maybe even tiny, depending on how old or irrelevant it seems.
And what does shrinking the image actually do to the text information it holds?
Well, first, it naturally uses fewer vision tokens. That's the efficiency gain, the whole point. But visually, what happens when you shrink an image of text too much?
It gets blurry, harder to read the details.
Precisely. That blurring isn't a bug here, it's the feature. It acts as that graceful, gradual loss of detail. You still capture the overall structure, the main topic maybe, but the fine-grained specifics get lost. It mimics how biological memory seems to work, following those decay curves.
So you're trading perfect recall for massive efficiency gains on older information, using blurriness as the mechanism.
Right.
That feels like a really different way to think about context windows and LLMs.
It's a huge conceptual shift, yeah. It offers a potential path towards architectures that could handle theoretically unlimited context.
Unlimited.
Because the system can dynamically manage the cost. It keeps the recent high-importance stuff in expensive high-fidelity storage, low compression, but the vast ocean of older context gets progressively compressed and blurred, making it computationally cheap to keep around. You get the feeling of near infinite memory, but you only pay the heavy quadratic cost for the small window of currently relevant information.
That ability to dynamically allocate the cost of memory based on its age or relevance, that's revolutionary for managing resources in these massive models.
It really is. And DeepSeek-OCR provides the empirical grounding for it. It shows, look, we can get anywhere from, say, 7x up to that 20x compression, depending on how much fidelity you need for different stages of historical context. It gives engineers actual numbers, guidelines for how to tune this trade-off.
So wrapping this part up, the big breakthrough seems clear. We can actually use images, the visual modality, not just for seeing pictures, but as a surprisingly efficient compression tool for text itself.
Yeah, it flips the script. Instead of just fighting the sequence length limit, it offers a way to fundamentally change the sequence length by using this visual compression.
And while DeepSeek-OCR itself was focused on, well, OCR as a proof of concept.
Right. It was proving the compression works for text reconstruction.
The implications are much broader. The research strongly suggests that by integrating these ideas, maybe combining text-to-image generation with this image-to-text decoding, We might eventually achieve something like 10x lossless compression for context in general AI system.
That's the potential long-term prize, yes. Imagine near lossless 10x compression.
So a final thought for you, the listener. Think about what that 10x compression could really unlock. We talk about AI agents, systems that process vast amounts of information. What if they could effectively remember everything, every document they've read, every conversation, not perfectly perhaps, but with older information gracefully blurred and compressed, making it cheap to retain? Could we see systems with truly persistent, long-term memory finally breaking free from today's restrictive context windows? That seems like the next frontier this kind of research opens up.